Okay, hi everybody. Welcome to Tuesday's lecture. So we have wrapped up the bulk of our physics course. So we're just kind of riding the wave, and pun intended, because we're talking about waves today. So we're riding the wave into the end of the course, and the majority chunk, I would say like 85 to 90% of first year physics 136. Has a very natural story that we tell. Like I could almost write a novel, like a mystery novel, with the first few chapters, because we started off with recognizing a phenomenon of motion, and we said, okay, well, it's too complicated at the moment to figure out what causes the motion, but assuming we see the motion, which is easy to see, where's it going to go? Okay, that was kinematics. And we said, all right, well, we've done that. Now I guess we have to go back and figure out what causes the motion. That was dynamics. The band-aid was energy for variable forces. And then we kind of realized, well, hey, hold on. We know what causes motion. We know where it's going to go, assuming there is motion, but what is motion? And then that was momentum. And then, you know, we're like on top of the world, cloud nine. We're like, hey, good, we got this. We can explain the world around us. We know motion. We know what causes motion. Where's it going to go? We got this. And then we kind of got struck down back to reality, realizing, oh crap, there's a whole realm we have neglected, and that was sort of the rotational realm, things rotating. And pretty prevalent things in our universe, in our day-to-day lives, rotate. I mean, the Earth is rotating, the Earth orbits around the sun, the moon rotates around the Earth. So like, you know, there's a lot of physics that we experience in our day-to-day lives that is a result of the rotation. We even get seasons, winter, summer, because of the precession of the Earth. So it's very important. And then if we were to retell all of our story again, all of the kinematics, dynamics, energy, momentum in the context of rotation. So there was a very natural story, a very natural plot line that sort of connected and motivated all these chapters. And now that we're finished that, we're just sort of doing something just discontinuous. We're going to move on to a topic called oscillations and waves, and it is still physics, certainly physics, but there's no logical next step. I mean, once we finished angular momentum, we could have pivoted anywhere. We could have pivoted to fluids, we could have pivoted to special relativity if we wanted to, we could have pivoted to oscillations and waves. The story pretty much ends at angular momentum. And just given the current curriculum at UTM in this physics course, the curriculum says we finish the class with oscillations and waves. This is sort of an introduction to, oh, why am I writing in gray? That's a weird color to write in. This is sort of an introduction to classical mechanics. And classical mechanics, we've touched on other parts of classical mechanics as well, like Newton's laws. But classical mechanics is really analyzing motions of systems of particles. I'm dumbing that down quite a bit. So if anyone's watching this YouTube video at a later time who's an actual physicist, please don't shit on me for dumbing down the classical mechanics that far. But anyway, we at UTM feel as though students should leave this class with a more holistic understanding of classical mechanics and you know, motion. So we're sort of tying in Newton's laws and motion into yet another kind of motion, not translational, not rotational, but oscillatory. And the reason why this is so prevalent and is even in the curriculum at all is because oscillations are everywhere in nature as well, not just invented in a physicist's brain, but naturally occurring in nature, as you will see later on, you know, when we do some examples. But anything that kind of has a rhythm to it is defined to be an oscillation. And for those of you who are in med or pre-med who are aiming for med school, hopefully you'll kind of this will resonate with you, because you know, a lot of systems in the body follow a sort of a sinusoidal or an oscillatory rhythm. So let's say like your heartbeat is not quite sinusoidal, but it's close, and there's a definite periodicity to it, and it takes on certain patterns and characteristics. And you know, a common diagnostic as a doctor is to listen for the heart rhythm to see if there's any heart problems. So, you know, there are themes in oscillatory physics that kind of relate to heavily relate to medicine, among other disciplines as well. So that's why we decided to end off the course with oscillations and waves versus something like, you know, special relativity, because special relativity is not as useful for the life science students as, say, oscillations and waves is. So there's the context. So without further ado, let's just jump into it. So here is a sort of table of contents of what we're going to go about doing. We're going to start by talking about simple harmonic motion in the context of things oscillating on a spring. That is the most common example of simple harmonic motion, but there are other examples of simple harmonic motion as well. But just for simplicity, to make sure we can get the concepts across to you guys effectively, we're going to try to not complicate the situations and use something simple that we're familiar with, like a spring. Like we all know a spring, Hooke's law, kx, F equals kx. So that's mostly why we use springs. They're just simple and easy to understand. The period of oscillations we're going to talk about as well. We're going to move into pendulums and then wave motion. So we'll see how far we get. Okay, so let's start with, let me zoom in a little bit so you can see. Oh, that was too far. There we go. Let's start with introducing what simple harmonic motion is and why we even get oscillations. So as the slide says, if an object is vibrating or oscillating back and forth over the same path each cycle taking the same amount of time, the motion is said to be periodic. So as you can see here, I've typed in a question. Why do we use the term periodic? And for those of you who have recently taken a calculus course, you may have also seen this phrase, periodic. Assume you have a periodic function f of x. And historically in math class or in calculus class, students don't really grasp, they don't fully grasp the term periodic. And then here we are reintroducing that term in physics class, and again, not really fully grasping what the term periodic means. So why do we use the phrase periodic? Periodic or period means that there is a certain length of time in which any pattern can occur, but after that length of time, the pattern repeats. So chemistry uses this term when they talk about the periodic table. You know, they talk about periods in the periodic table, and the reason why they call them periods is because, you know, within a certain period, there's a defined pattern, and then when you move, you know, to the next one, it repeats. So for instance, a pattern in the periodic table would be the atomic radius will decrease as you move to the right. You know, so like, let's say, like sodium, for instance, has a smaller radius compared to the bottom of the periodic table, like cesium, which is a larger atomic radius. That's a pattern that you can depend on. You know, things like that, or even valence charge is another pattern that you see in the periodic table as you move to group number, like larger group numbers. Like sodium has a +1, and then as you move to the right, you get a more negative valence. So like there are these sort of patterns that are in the periodic table, and they call them periods. And you know, we have similar notions in math, and we have similar notions in physics. So in this case, we call it periodic because if you were to elongate a mass on a spring, let's say by an amount x, then according to Hooke's law, you have a force equal to k delta x, and it's a restoring force. So if you elongate a spring, the spring's going to pull backwards because the spring wants to return to its unstretched length. And so this block is going to feel a force to the left, and then it's going to come back to equilibrium, but it's going to have a velocity, so it's going to overshoot. So it's going to overshoot, and then it's going to come back, and it's going to oscillate back and forth, back and forth, back and forth. So because this object, the motion of this object repeats over time, then we call it periodic. So any function that has a pattern that will repeat over a certain length of time, we call it periodic. It doesn't have to be sinusoidal. It doesn't even have to be continuous, to be completely honest. Periodic just means the pattern will repeat, dependably repeat. So this all starts with, in the context of a spring anyway, this all starts with Hooke's law. So that's what we're going to analyze here. So just to recap from Hooke's law, we know that the minus sign on Hooke's law, let me change my color, the minus sign in Hooke's law indicates that it's a restoring force. So if you elongate something to the right, the force is directed to the left, right? F equals like minus kx technically. Now, the negative sign we usually account for in our free body diagram. We draw the diagram, or we draw the direction of the spring force in our FBD, and based on the FBD, we can assign a coordinate system, and then the plus minus signs take care of themselves because we just use the arrow directions in the FBD. So the minus sign is more of a convention than anything. Oops, more of a convention. K is obviously the spring constant. We've been over this right from the beginning of the course, in fact, with the intro lab, or the intro assignment. The spring constant K is measured in newtons per meter, which means, let's say the spring constant is 100 newtons per meter. The way you physically interpret that spring constant means you need 100 newtons of force to elongate that spring 1 meter. And we learned this with energy. This is very, 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 very important. Big star here, very, very important. The force is not constant. And this is a big motivator for why we even needed energy concepts. F equals kx means as the object moves, either forward, backwards, the x is changing. The position or the elongation is changing. And that means the resulting force will change, which means the resulting acceleration will change, which means all of our analyses we have to throw out the window, because, you know, kinematics, dynamics, they're all for constant accelerations. So, you know, then we have to move into energy and sidestep acceleration altogether, and then look at conservations of energy. So that's a really important concept, is that the spring force is not constant. Okay, so let's look a little bit at the motion, and I've already kind of described this. So after we kind of break down these panels A, B, C, D, and E, we're defining some variables that quantify motion in this sense. And then we're going to take these variables and try to come up with equations that have them inside of them. So here, that depicts, let me zoom in a little bit for you. It's a little bit blurry when I zoom in. So here is the equilibrium position, x equals 0. That's when there's no net force. So if you were to compress the spring and you compress it a distance capital A, then that means your x coordinate is now at negative A, because you're compressing it, you're pushing to the left a distance A meters. So your x coordinate is negative A. Now at that time, before you let go, the initial speed is 0, right? Because you haven't let go yet. But there's a net force on it. The net force is kx. Or in this case, because it's at A, I should say the net force is ka. So this will actually have an acceleration of ka over m. Now, if there's an acceleration, then that means there's a force, and if there's, you know, motion, it's going to move forward. So if I let go, it's going to take all of that spring energy that it had at point negative A, and it's going to use that stored kinetic energy, that stored spring energy, and transform it into kinetic energy, and that's what carries the block forward. Now, at equilibrium, as we know from dynamics, equilibrium means the net force is equal to 0. Now, just because the net force is equal to 0, meaning that there's no acceleration, because F net equals ma, 0f, 0a, just because there's no acceleration does not mean there isn't motion. You can be traveling forward at a constant speed and have no acceleration. That is precisely what's happening here. At the point x equals 0, the block will have forward inertia. The block will have a non-zero velocity. That's how it reached the equilibrium position. It's like sliding into home base. It has a forward inertia. So even though there's no net force at x equals 0, the block will actually continue forward. And then as it continues forward, then x is no longer 0. X becomes positive, and the spring starts to pull backwards. And if the spring starts to pull backwards, as we see here in the next image, as the spring starts to pull backwards, there is a negative acceleration with a forward velocity, which means the block starts to slow down. And then it will continue to slow down until it comes to rest. And using conservation of energy, it's fairly easy to see it will come to rest when x is equal to positive a. It's equal on both sides. And then it'll repeat. The spring is elongated here by a distance positive a. So there's going to be a backwards force. So then it's going to pull it backwards. And then it's going to overshoot the equilibrium again because it's going to slide into home base with a negative velocity or a inertia pointing toward the left. And then overshoot equilibrium again, and then end off where it started. It'll end off at x equals negative a, right where it started, and then the whole process will simply repeat. That's why it's called periodic, because these 5 stages, let me zoom out a little bit so you can see them all in one go. These 5 stages, A, B, C, D, E, that's what happens kind of in the middle. And that motion that happens in the middle will repeat after a certain length of time. That's why it's called periodic. Now that we have a better understanding of kind of what the motion is, this sort of repetition, periodic motion, what are some key defining variables or quantities that we can list that if we were to happen to know all of these quantities, then we could know every part of the system? That's really what we're after here. So displacement is obviously a big one. You know, we're trying to quantify displacement. Another attribute of the system is something we call amplitude. Amplitude would be the largest displacement. Yes, displacement as a function of time will change. Sometimes it's at equals 0, sometimes it's at x equals a, sometimes it's at x equals 0.5. Displacement will change with time. Amplitude does not change with time. Amplitude is defined to be the largest displacement. And you know this notion from math class. We've talked about amplitude of sine waves starting in, I believe, grade 10 or grade 11. Definitely grade 11 for sure, maybe even grade 10, depending exactly what school you're from. So you should have a notion of what amplitude means from math. We use the terminology cycle. So one cycle means the motion, all parts of the motion in one complete period before it repeats. Every unique part of the motion. That's what a cycle is. So it's full to and fro motion, meaning like forward and back. Once it starts to repeat, the cycle is done. The verbal phrase period, or the variable period, is the length of time in this case, the length of time it takes to complete one cycle. We should have known that from math class and previous usages in this class. And frequency is how many cycles occur per 1.0 seconds. And these two are inverses of each other. The period equals 1 over the frequency. If the period is half a second, meaning you have one complete cycle in 0.5 seconds, then how many cycles do you have in 1 second? Well, you've got 2, 1 over a half. So period and frequency are inverses of each other. Okay, so that's what simple harmonic motion is. Simple harmonic motion is a vibrating system where the restoring force is specifically proportional to the displacement. So what does that mean? I think the best way to sort of explain what that means is to explain what it's not. Not every oscillation is simple harmonic motion. Simple harmonic motion means that the restoring force is linearly proportional to the elongation, or the distance away from equilibrium, linearly. So, for instance, gravity, we know from Newton's law of gravity, is inversely proportional to the distance squared. If you had something, like let's say you had the Earth, and let's say you were able to do it, what all the movies claim to do, you can drill a hole right through the center of the Earth, which is demonstrably impossible to do. If you could drill a hole all the way through the center of Earth, and you were to drop a rock or something down, then as the rock falls, the gravity will change because it's getting closer to the Earth's surface, obviously. Actually, once you're inside of the Earth, it's no longer GMM over R squared. It's something else. You need Gauss's law for gravity. We won't get into that. I believe it's actually, well, it's different than that. Point being, though, the gravitational force is no longer proportional to its position away from the Earth's center. It's something different. Now let's pretend for a second it's GMM over R squared. That would mean as you get closer to the Earth's surface, we're going to pretend this equation is true for inside the Earth, which it's not, but let's pretend just for sake of argument that as you get closer, the force of gravity is going to increase as a function, and because R is getting smaller, it's going to increase according to 1 over R squared. That means the force is not proportional to the displacement. It's inversely proportional to the displacement squared. So it still will be a type of oscillatory motion. It will fall, it will cross through the center, and it will reach the other side, quote unquote China, as the movies say, and then it will come back up, and it'll oscillate up, down, up, down, up, down. But even though it's oscillating, it will not be simple, because the force responsible for the motion is not linear. So simple harmonic motion, specifically simple, actually let me underline that in red. The word simple harmonic motion simply means that the force is proportional to the displacement. Okay, moving right along. So let's do a concept check with you right now. Let me launch the poll. Let me see your poll, launch poll. Okay, and let me shrink the slide so you can see it. Okay, so here's the question. A mass on a spring is known to be in simple harmonic motion, and it has an amplitude of A and a period capital T, you know, for that silent T in the word period. Physicists, I don't know. We don't know how to spell, what can I say? What is the total distance traveled by the mass during the time interval T? 0, A over 2, A, 2A, 4A. So 10 of us have answered. 13, 15, 18, 20. Oh, wow, it's going fast. 25. In one complete cycle, what is the distance traveled by the block? (33 out of 47, 34 out of 47. We're getting there. Also, might I add, as we're recording and you're watching this later perhaps, there's only 47 students attending the lecture out of 150. That's probably not a good ratio, so let's see what happens with the test on Saturday. Okay, there's 42 of us out of 47. I'm just going to end the poll here. And here's the results. So the Democratic winner is D. The Democratic winner is the total distance traveled after a time interval T is 2A. And 50% of the people voted. The next, for that one, the next winner is 21%, so less than half. It was E, and then it was C for 12%, B for 10%, and A for 7%. So let's look at this. The mass on a spring has amplitude A and period T. What is the total distance traveled by the mass after a complete cycle? So a complete cycle means it does all parts of the motion once. So let's look back at my drawing up here. Let me erase all my markings to make this clear. Let's see here. So we have negative a to 0. Okay, so that's a. And then we had 0 to a, so that's plus a. And then we had a back to 0, so that's another a. And then we had 0 back to negative a, so that's a fourth a. So the answer, in fact, should be E. The answer should be 4a. The distance traveled in one complete cycle is 4 times the amplitude. So I guess it's a good thing we don't let science be subject to democracy. Democracy isn't always correct, as we've sort of seen in some previous elections in various parts of the world. Democracy isn't always the greatest thing. I mean, it's definitely better politically than many alternatives, but this is definitely why we cannot have science be subject to opinion. Anyway, so the answer is in fact E. So 21% of you got that correct. So that's good that we're doing this, because it means that there's some misconceptions that we need to hammer out. Okay, so I'm going to stop sharing the results so you can get your screen back. Oh, look, we have another one. So because the first one was so shocking of a result, let's do the next one. Let's see here. Relaunch the poll, continue. Okay, so you should see the poll. Oh, what's happening? There you go. Wait, it's not relaunch poll, continue. There we go. Okay, so you should see a new poll now. Let me make the question smaller so you can see it on your side. A mass on a spring is known to be in simple harmonic motion and has an amplitude A and a period T, just like before. How long does it take for the mass to travel a total distance of 6a? How long does it take? A half period, 3/4 period, 1 1/4 period, 1 1/2 period, or 2 times period? We're traveling a distance of 6a. How long does it take? Half period A, 3/4 period B, 1 1/4 period C, 1 1/2 period D, 2 periods E. So we have 35, 36, 38, 39. So that's right close to where we were last time. So I'm going to end the polling and I'm going to share the results with you. So there we go. Here we have a pretty clear victor. 75% voted D. D was the Democratic winner last time. So maybe you guys are just, you know, tunnel vision when you're voting. The answer's always D. You know, what do they say with multiple choice tests? If you just answer D for everything, you're like statistically bound to get like 25% correct. Think about that math. That should make sense. If there's only, well, if there's only 4, I guess if there's 5 answers, then I guess it's 20%. Anyway, that aside. So you're wanting redemption for answer D. Let's see if this makes sense. Let me stop sharing the results so you can get your screen back. So here, 6a. So we know 1 complete cycle. We know 2a forwards, 2a back, 4a for, and we travel 6a. So we travel 4a plus 2a, which means we travel 1 period plus a half a period. So the answer is 1 1/2 periods. So the answer is D. So D came back for a redemption. I'm glad to see D had some redemption. Okay, so our goal, just like with kinematics, is to obtain an equation of motion, right? With kinematics, way back in May, we started our story with saying, hey, look, we noticed there was motion. Where is the object gonna go? That's what we're doing here. We're noticing a new type of motion. It's not translational, it's not circular or rotational in any way, it's oscillatory or periodic. Now that we've identified a new kind of motion, obviously the goal as a scientist is to quantify, measure, build a model, predict. So let's see if our goal is to develop some equations of motion. Let's see if we can do that. In order to do that, we have to investigate properties of this motion. So let's start with energy, just because it's a little bit easier than doing the, jumping right to the equations of motion. So if we go to energy first, we're only doing energy first, by the way, because we've done energy of a spring in a previous chapter. So we're piggybacking, we're pulling in prior knowledge from a previous chapter. So when the spring is fully compressed, then what has happened is we have stored potential energy in the system. Not gravitational potential energy, but spring potential energy. You're storing energy in the spring. And when you release it, then the spring can partially elongate and the object moves forwards. Now, there are many times when the object is moving forward, but the spring is also partially compressed or elongated. So the total energy in a spring system is going to be the sum of the kinetic, oh boy, that's a terrible K. It's going to be the sum of the kinetic energy plus the spring energy. So that if you measure the current spring energy at a moment in time t, and you measure the current kinetic energy at the same moment in time t, and you add them together, that will give you the total energy of the system. Okay, so what does this mean? Well, originally, when you have the block that has been manually pushed, someone has pushed this block into place, and it's located at negative a, x equals negative a. So the amount of energy in the system is the sum between kinetic and potential. This object isn't moving because you're holding it at x equals minus a, so there is no kinetic. Kinetic is at 0, and all of the energy is sitting at potential, 1/2 k a squared. As it moves, the spring potential energy slowly gets converted. I shouldn't say slowly, it gets converted all into kinetic energy. And at the moment of equilibrium, x equals 0, which means the spring is neither compressed nor stretched. So the spring energy, 1/2 kx squared, x is 0, which means there is no potential energy in the spring anymore. So all of the energy flows into the kinetic energy. So this means the object is actually going to be moving the fastest, maximum velocity. The object is going to be moving the fastest as it crosses the equilibrium position. So that's an important note about its behavior to make for yourselves. That in simple harmonic motion, the object is traveling fastest as it traverses through the equilibrium position. And then it continues through the equilibrium position to the location x equals a, and then the reverse happens. All the kinetic energy that it had then gets converted back into potential energy, and then now it's momentarily at rest at the other end on the right-hand side. And then the whole process repeats. Of course, at some location somewhere in the middle, where it's not necessarily at x equals a and not necessarily at x equals 0, the energies are shared. There will be a point in time when they're equal. If you want, that'd be a fun little side question. You could solve for the location x at which where the speed and the kinetic energy and the spring energy are equal to each other, or you don't have to. It's up to you. Anyway, they will share. That's the trade-off. That's what panel D is showing, is that somewhere in the middle, not at negative a, not at 0, not at positive a, but somewhere in the middle, the energy is shared between the two sources, spring and kinetic. Okay, so we see here that if you're in the problem or in the experiment or in the real world, if you happen to know what the amplitude of the oscillation is, then it's easy to determine the total amount of energy in the system, because the total amount of energy is constant. The total amount of energy is the same in panel A, it's the same in panel B, it's the same in panel C, it's the same in panel D. The total energy is constant. However, depending on what you have and what you don't have in terms of variables in the problem, it might be hard to find what the total amount of energy is. So here's where you can use a concept. Because the energy is constant at each point in time, if you know the amplitude, then that means way back at the beginning, when the object is at rest, sitting at negative A, or even at positive A, depending if you want to start with it compressed or start with it elongated, then all of the energy is sitting in the spring, which means 1/2 Ka squared is E total. So that's what the first bullet point here says. If you happen to know the amplitude, then you immediately know the total amount of energy in the system. Okay, using this setup, you can actually solve for the velocity of the object at any given point. And I don't really expect this formula to be useful in this class. However, the interesting thing is, if you set x equal to 0, then x equals 0 means there is no energy being allocated to the spring, and thus all the energy gets transferred into kinetic energy. So here, you can actually solve mathematically for the maximum speed, which we know the maximum speed occurs at x equals 0 as the object travels through the equilibrium. But here you can actually very easily derive a formula for the maximum speed, and all you need to know is the amplitude of the system. So a great question, like a great multiple choice question or a fill in the blank question on a test or an exam, could be something like, if I double the amplitude of a simple harmonic oscillator, how does the maximum velocity change? Well, here you see, if you double the amplitude, you simply double the velocity. It's fairly straightforward. Now, I could also say something like, if I double the mass, how does that change the maximum velocity? Well, if you double the mass, you don't have the velocity. Not quite, because m is underneath the square root sign. So it's a pretty fun formula, and it's not only is it fun because it's physics and you're using basic math to describe the world around you, it's actually fun because it's quite powerful. You can make a lot of very quick deductions about oscillatory motion by just knowing simple relationships. Okay, so I talked about energy. Let's see how many of you were listening. So I'm going to relaunch the poll. And here's the question. Let me shrink it so you can see. Oh, come on. So you can see the question. A mass oscillates in simple harmonic motion with a known amplitude of A. If the mass is then doubled, but the amplitude is unchanged, what will happen to the total energy of the system? A, total energy will increase. B, total energy will not change. C, total energy will decrease. If I knew how to hum properly and if I could carry a tune, I would hum the Jeopardy theme song right now. Maybe I should just like find a ringtone with that and play it on my phone while we're waiting for students to answer these. So we've got 33 responses out of 47, 35 responses out of 47. Okay, 38. This is about where we were last time. I'm going to end the poll. 40, 42. And no, we seem to be frozen at 42. So I'm going to stop the polling and share the results with you. So here we are. It looks like 74% of you say B, the energy will not change. And we have almost equal response rates for A and C at 12 and 14% respectively. So we have an overwhelming democratic winner of B. I'm going to stop sharing the results. Let's see kind of what is happening here. So we said that the total energy could be known by 1/2 Ka squared. And we know the maximum speed. That is true, that the maximum speed is root K over m times the amplitude. That's true. But the total energy is given by 1/2 Ka squared. Nowhere in there is the variable m. So you can double m, you can have m, you can multiply m by 1,000,000. That will not change the total energy of the system, because the energy of the system is only the energy stored in the spring, which is 1/2 Ka squared. All that will happen is if you double m and you keep the same amount of energy in the system, then that means the maximum velocity will obviously be slower. And that should make sense to you intuitively, because if the maximum velocity was the same, then it would be the same speed but for a larger mass, which would increase the kinetic energy, which wouldn't make any sense if the spring energy is unchanged. So this is a real testament to the power of conservation of energy. All you're doing is you're compressing a spring and you're changing what mass you put in front of it. Just because you put a larger mass in front of a compressed spring does not mean you change how much energy the spring itself has. Okay, so the answer there is B. Okay, let's do another one. Poll, relaunch poll. Oh, I gotta make the slide smaller, don't I? Come on. Okay, oop, too small, maybe. So there we go. Here's a question. A mass on the end of a spring is in simple harmonic motion that has amplitude A and period T. At what point in the motion is V equal to 0 and A equal to 0 simultaneously? At what point in the motion is V speed equal to 0 and A acceleration equal to 0 simultaneously at the same time? 10 of you have voted, 12 of you have voted, 16, oh, now we've shot up to 25. I'm so glad we're doing these. These are beautiful questions. I know you can't see the results live as they're coming in, but they are actually quite interesting. 39 of you have voted, so we're kind of right where we were before. 40 of you have voted. 41. Okay, I'm gonna hit 42. Okay, I'm gonna stop the polling and share the results. So as you can see, we actually have a fairly uniform distribution. I mean, not mathematically uniform, but visually uniform. A got 24% of the votes, C got 40% of the votes, and E got 33% of the votes. So I guess it's a little bit normal, like Gaussian, but it kind of looks like a flat line. There's a substantial number of votes for A, C, and E. So let's see what's going on here. Democratically, C won with 40%. But let's see if that's actually correct. So we want the speed, oh, come on. We want the speed to be 0 and the acceleration to be 0. Well, C lists the answer x equals 0. At x equals 0, though, that's going to be where the maximum speed occurs. That's where all of the potential energy is transformed into kinetic energy. If we scroll up just a little bit, well, let me stop sharing the results so you can get your screens back. If we scroll up just a little bit, we know the maximum energy will occur. Where did we have that slide? Maybe it was down here, sorry. We know the maximum, oh yeah, here it is. We know the maximum speed will occur at the middle, or at x equals 0. So C can't possibly be the correct answer here. Oh, we did that one. C can't possibly be the correct answer because speed is a maximum here. So V equals maximum. So C can't be right. Now, what is true at x equals 0 is that the acceleration does equal 0 there. Because this is true because x is equal to 0. So F equals kx implies F equals k times 0, which means the force is equal to 0. So if there's no force, sorry, no net force, there's no acceleration. So it is true that A, but V is a maximum. It's quite the opposite of 0. It's a maximum. Now, if B can't be right, because if x is greater than 0 but less than A, then the spring, the x value is non-zero, which means there's a force, and if there's a force, that means there's an acceleration. So A isn't 0. Oops. A isn't 0, and likely V is also not 0. Now, at x equals A over here, it is at rest. Because if there was a non-zero velocity, then it would just keep moving to the right. It would keep moving forward, and then A wouldn't be A, right? A wouldn't be the amplitude if there was a larger x value. So by definition, since it's A, the amplitude, it never goes beyond that, which means at that point in time, momentarily, the speed is 0. But the acceleration is not 0 because F equals Ka, which means your acceleration is going to be nope, it's not. It's going to be Ka over m. So it's a non-zero acceleration. So the answer is in fact E. None of them. There is no place where both the acceleration and the velocity come to 0. Now, if you wanted a quicker way to come to that conclusion, think about this. What does it mean if the object is currently not moving and there's no acceleration on the object? It means the object will just stay there. My car is in the driveway right now. It's not moving. The velocity of my car is 0, hopefully. And the acceleration of my car is 0, which means a second later, its velocity is still 0. So when a velocity is 0 and an acceleration is 0, that object is not only not moving, it will remain stationary. So then you just have to ask yourself, is there a point in time where this object comes to rest and stays at rest? No. This object oscillates back and forth forever. It never comes to rest and then stays at rest. It momentarily comes to rest, but then a second later, or not even, like a moment later, it starts to move again. So there's the answer, E. Okay. So let's move on, talk about more attributes of this motion. We are trying to build a mathematical formula for this motion, but before we do that, we're trying to investigate certain properties of this motion. So we've already investigated the repetitive nature of this motion. We call it periodic or oscillatory. We also talked about how energy can predict certain features of the motion, how the total energy is quantified by 1/2 Ka squared, and how the maximum speed occurs at the middle or at the equilibrium position, and how the acceleration and velocity are never both 0 at the same time. The next piece of information is how to measure or how to think about the period, the time of one complete cycle. Now, I am a huge proprietor of trying to show students where equations come from. Unfortunately, I am fully willing to acknowledge when that derivation is above your head. Now, this is a beautifully simple equation. The period of oscillation of a mass on a spring is given by 2 pi times the square root of the mass of the object divided by the spring constant. It's a very simple equation. And thinking about the relationships in here is fairly easy. If you quadruple the mass, you're only going to double the period because mass is under the square root sign. If you find a stiffer, a stronger spring, let's say you found a stronger spring that had a spring constant that was 4 times as large as the old spring, you're only reducing the period by a factor of 2, meaning you're only making it go faster by a factor of 2. And as you can see, the frequency is just the flip, the one over that. Now, as simple as this equation is, the derivation of this equation is actually very complicated. I will outline, and it's not impossible for someone in first year to do this. It's just very, very top of the line, I would say. So I will spell this out for you, but I will not do it. So first, you need to solve the differential equation. I don't know why my screen is lagging even on my end. I can only imagine it's lagging on your end as well. So first you have to solve a differential equation. Specifically, you have to solve F net equals MA. And then after you solve that, you have to make a small, actually no, for a pendulum you make a small angle approximation. For this one, you don't. So you just have to solve this, a second order linear ODE with constant coefficients. And that is something that is beyond the scope of this class. And quite frankly, it's probably halfway through the curriculum of a second year differential equations class. So I obviously won't do that for you here because it'll just go over everyone's heads, and it's not in the curriculum anyway. So I'll just say that you have to solve the equation of motion using differential equations. But once you do that, you get a fairly simple relationship here, and you get period equals 2 pi times the root k over m. So even though this is a derived equation, for this class, it'll be provided to you on a formula sheet, and you are not expected to derive this equation. I'm just saddened by the fact that I'm not able to show you the derivation and have students appreciate it, because it is, just trust me, it is a lot of differential calculus that is beyond the scope of this class. Okay, we are a millimeter away from coming up with a mathematical expression for displacement. I mean, with kinematic equations, we started with acceleration and we integrated twice, if you recall our discussions with kinematic equations. We started with the acceleration being a constant, integrated once, we got a linear velocity, integrated twice, we got a quadratic displacement. And I know this is not a calculus class, so that derivation of integrating twice to get a quadratic is not tested, but hopefully coming from a recent calculus class, this being a summer class, you would have had calculus recently, most of you, you can kind of relate to how easy those two integrals are. We're going to do something really in the truest nature of a physicist. Believe it or not, everyone thinks physicists really like math and blah, 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 blah. Yes, it's true. We use a lot of math, but we avoid using math whenever humanly possible. We're good at math, we just don't like it. So we're actually going to cheat the system here. We're not going to start with the acceleration and integrate twice. Reason being, it's not a constant acceleration. Now, if you knew calculus, it wouldn't be hard to integrate twice because you know how to integrate variables, but whatever. We're just going to bypass the calculus altogether, and we're just going to reverse engineer what the formula is for displacement by just watching with our eyes. It really is a beautiful example of a physicist hard at work. So I'm going to show you a video shortly. I'm hoping the video isn't too choppy on your end. I'm noticing recently as I'm writing, the letters that are appearing on the screen lag behind my pen, and that's for me, I'm live. I can only imagine it's a little bit more of a lag for you on your end. So I'm hoping the video comes through reasonably smoothly, but let me set it up for you. That way, even if it's choppy, you have some context. Let's say we have a mass that is on a spring, and you set it into motion. Let's say you just kind of pull it up or you push it up or pull it down just a little bit to give it a non-zero amplitude, and then you let go. The spring is kind of going to oscillate up and down. Kind of like a vertical spring system instead of a horizontal spring system. As it oscillates up and down, our goal is to determine a mathematical equation to represent the displacement as a function of time. So here's the trick. Here's the physicist trick that mathematicians hate that we do all the time. Thought experiment. What if we had a piece of paper on a roll behind the mass? And let's say we taped a pencil or a pen or a Sharpie to this object, and as it moves across the paper, it draws, it leaves a line. And what we can do is we can roll the paper as time goes on, and you'll see the pattern that is formed on the paper. That's the video I'm about to show you. So if it's choppy, please just understand all that's happening is there's a mass on a spring oscillating vertically up and down, not left and right, vertically up and down, and it's able to draw on a piece of paper that somebody is pulling forward. So let's have a look at that now. Oh, I just realized I have to change which screen I'm sharing. Just give me a moment. Okay. Okay, welcome back. I don't know if it's my internet that's causing it to be slow or if the computer is doing something in the background. So I'm gonna leave my camera off. Hopefully that helps speed things up and it makes the computer less worried that it's gonna crash. Hopefully not seeing me is not too much of a negative. I don't know. Anyway, so what you saw in that video was a spray can being attached to a spring oscillating up and down. And you can clearly see that when the paper is pulled forward, what kind of motion is a result of that? You actually see it's a sine wave or a cosine wave. We call this sinusoidal motion. Sinusoidal means it can be modeled by either a sine wave or a cosine wave. So what we've done is, and I will tell you quite frankly, physicists do this far more often than you think we do. We try to bypass the math as much as humanly possible, and we say, oh crap, you know, we've got to start with the acceleration, integrate twice. I don't really want to do all that work. Let me just set up something in real life and watch the motion, and I'll reverse engineer the formula. This happens all the time. It's actually quite beautiful. It's one of the only hardcore sciences that just sort of says, yeah, screw it, the math is too hard. Let's not do it that way. Kind of ingenious, really. So we saw that it was some sort of sinusoidal wave. Now, all of the examples we've been talking about up until now have assumed that we start with an initially compressed or an initially elongated spring, meaning all the discussions we've been using up until now, the object starts at the maximum. So between sine and cosine, which of those functions has the object starting at a maximum? Well, a cosine looks like this, and a sine looks like this. So if we're starting our object with a position that is the maximum, then we inherently want to use a cosine. That doesn't mean there's another question where it starts at rest and you sort of give it a punch or you give it a bit of a kick. So the initial location is x equals 0, but you're giving it an initial velocity. That's okay too. That would mean you're modeling it with a sine curve. But anyway, we're going to use cosine just to keep things simple. So what parts of, well, cos, an arbitrary cos function is a cos omega t. That's just arbitrary. That's just any old cosine function. In math class, you might say y equals a cos kx in math class. Now, in our case, the independent variable is time, and the dependent variable is location x. So that's why I'm saying x is over here and t is over here. So, what is omega? Well, you might recall from grade 11 math that k represents the horizontal stretch or compression of the graph. And k in math class, k is calculated by 2 pi over the period. Well, same pattern sort of fits. Instead of k, we use omega because we're not using x as our independent variable, we're using time. So here we know cosine takes in a radian. So omega times t has to give you a radian. So we know t is measured in seconds. So something times seconds has to give you a radian. So obviously the answer there is going to be radian per second times second gives you a radian. So that's how I know it's omega. And we've seen omega before. It's the angular velocity, the rate at which the angular displacement is changing. Omega. It's the same omega we learned from just in the previous chapter. So we can represent omega with 2 pi frequency or 2 pi over the period. As I mentioned before, we knew that from math class, we learned this in grade 11 math, that the value in front of that the coefficient in front of that independent variable is 2 pi over the period. So we know that omega is going to be 2 pi over the period. We also know the period and the frequency are inverses of each other, so you could also say it's 2 pi f, whichever one you want. And there you have it. We have bypassed all of the math. We haven't solved any differential equation. We haven't used calculus. We literally just pulled some string and pulled some paper across a spray can that was bouncing up and down, and we were able to just know that the mathematical expression for displacement is a cos omega t. Bam! That simple. We now have our equation for displacement as a function of time. So much easier than what we got with our kinematics equations. Okay, my computer's behaving now, so I'm going to try to turn on the video again. Hopefully it doesn't bog it down. Okay, hi, I'm back. Okay, so here, where does that leave us? Okay, well, we know that there's different parts of the graph. So like, how is omega in period measured? If you happen to have the graph, period is the time it takes. What color? Oh, I gotta change my color. Period is the time it takes to complete one complete cycle. So this time here to this time here, right? Peak to peak would be one cycle. If I go beyond that, I'm just repeating myself. So that is how you see. If you had a graph, recall from grade 11 math, grade 12 math, first year calculus, that is how you find period. And k, if you look at the formula in math, y equals a cos kx, that's a math equation traditionally using x's and y's. K represents a horizontal stretch and compression. K in math class is 2 pi over the period. If period gets longer, then that means you're horizontally stretching the graph. So if period gets longer, then that means T goes up, which means the fraction goes down and K gets smaller. So you'll remember from math class that if K is less than 1, it's actually a horizontal stretch. And if K is larger than 1, it's a horizontal compression. The reason for this is because period is on the denominator. So the value for K is inversely proportional to the period. And in our case, it's the same thing. We have omega equals 2 pi over the period. So as the period gets larger, the motion gets slower. If it takes longer, if the period gets longer, then that means it physically takes more time to complete one cycle, which means it's traveling slower. Okay, so with that said, let's see. Oh, I have something else popping up on my screen. There we go. Let's see if we can do this poll. Relaunch question. There we go. Okay, so let me shrink this so you can see it. A glider with a spring is attached to each end. A glider with a spring is attached to each end, oscillates with a certain period. I think that's a bad sentence. There's some sort of typo in there. If identical springs are added in parallel to the original glider, what will happen to the period? If you have to, you can draw a little bit of a picture. So a glider let's see, a glider is attached to, a glider with a spring attached to each end. So there's a spring on this end, there's a spring on this end, and we can set this thing into motion. So if I pull the glider to one side, this spring is getting compressed, and this spring is getting elongated. The question says, if I add a second set of springs in parallel, so instead of having one spring on each side, there are now two springs on each side, what will happen to the period? Increase, decrease, increase, no change, or decrease? Also, I will remind you, physicists are not good with words. I saw everyone was like not really voting until I drew a picture. That is totally normal. That is why every time I say you're doing a problem that you're kind of unsure of, draw a picture. For the love of physics gods, draw a picture. One person is a rebel and voted E. Okay, 39 of you have voted, 40 of you have voted. Okay, it looks like we've plateaued, so I'm going to stop the polling and share the results. So democratically, we have an answer of B as a winner. 53% of you said it will not change. And then the next answer is 33% of that the period will decrease, and 13% will say that it will increase. Let's see if this makes sense. So we know the period is going to be 2 pi times root k over m. No, is it m over k? What was the formula there? Yeah, m over k. Okay, so here they're saying if we add springs in parallel, what are we doing to the overall spring constant? Well, before, if you draw a free body diagram, we had, if we compressed the right spring, then we would actually be creating a spring force backwards. And if we elongated the left spring, we would have a restoring force backwards as well. If we added 2 springs, then what we're doing is we're adding 2 more forces in the same direction. So what we're doing is we're actually doubling the spring force. Ergo, we are doubling the effective spring constant. So we are actually increasing the K value, which means we are decreasing the period. This should make sense. If you add more springs, you have more force on the object, and so you're able to get the same amount of mass moving quicker. And if you're able to get the mass moving quicker, then you will decrease the period. So this is the sort of intuition I'm hoping you guys start to build, is that, you know, the exact equations you may not be able to remember, you might have to look them up, but the relationships you should be really solid on. If I make the spring constant larger, if I make K larger, think to yourself intuitively, would that speed up the period? Would that speed up the object, or would that make the object go slower and increase the period? These are really the things you have to start thinking about. Okay, enough of spring systems. My brain is going crazy with all the spring systems. Let's move on to another type of oscillation, pendulums. You've seen sort of pendulums before. Hopefully, they're around. For those of you who have parents that have grandfather clocks, by the way, grandfather clocks are very rare nowadays. You know, when I went through undergrad, a lot of people still had grandfather clocks. So, you know, physics profs use grandfather clocks in their class quite frequently because they were so prevalent. But now, I think, you know, almost 2 decades later, not prevalent anymore. So it's a little bit iffy. But anyway, I'll do a grandfather clock question with you later. But what is a pendulum? All a pendulum is you have a mass that is located at the end of a massless string. Now, of course, there's no such thing as a massless string, but relative to the weight at the end of the pendulum, the weight of the string is negligible. Now, there's something called a physical pendulum where the rod or the string is actually a rod and the mass of the rod is significant compared to the mass at the end of the rod. We will not be studying physical pendulums in this class. So if you're doing homework questions and you see the terminology physical pendulum, you can skip it. We won't be doing those. So if you take a pendulum or an object on a string and you sort of lift it up at some angle theta, and you were to let it go, obviously it would swing. This is not a hard concept to figure out that it's going to happen. What force is responsible for the swinging back and forth motion? Previously, the back and forth motion was forced by the spring, meaning it was Hooke's law, Kx, that was responsible for the simple harmonic motion. Here we do not have a spring. So what force is responsible for this oscillatory motion? And the answer is gravity. We see that, let's say the pendulum was displaced at a 90-degree angle. Well, then gravity always acts straight down, and 100 gravitational vector is pointed in the same direction as the displacement at this location being straight down. However, when the pendulum is at the lowest point, gravity is still acting straight down, but the displacement is to the left. And no component of the gravity is acting to forward or to accelerate that mass. And the diagram that we see originally, before I drew all over it, is an intermediate. And it shows you that the direction of velocity, the tangential velocity, is currently sort of down on an angle, And the force responsible for this is a component of the gravity. It is the sine component of gravity. Now you can figure this out fairly easily from a free body diagram. Right, here's tension, here's theta, here's gravity. And what you're doing is you are breaking gravity down into components. So we want, if this is theta, theta is the same here. If we want the opposite side, then the opposite side is going to be mg sine theta. So that's where the sine theta comes from. Now, this means that the amount of force that is responsible for the motion is proportional to sine theta, meaning the bigger the theta, or should I say the bigger the sine theta, the bigger the force. Now, if you recall what sine theta looks like like this. So sine theta gets bigger as theta goes between 0 and 90 degrees. You can see that in this problem here. When theta is 0, when the pendulum is right down vertical, theta is 0, which means sine theta is 0. And according to this here, mg sine theta, you'd have mg times 0, you'd have no force in the direction of motion. You can verify this by looking at the diagram. The direction of motion will be to the left, gravity is down, there is nothing pushing it forward. Inertia is carrying it forward in the same way that inertia was carrying the block through the equilibrium position. But at the equilibrium position, at theta equals 0, there is no force pushing it forward. Now, we said the definition of simple harmonic motion, let me actually write this down for you because it's going to be important. Recall that simple harmonic motion, that should be an H, simple harmonic motion, the restoring force is proportional to the displacement. Well, our force equals mg times sine theta. The force is not proportional. Oops. The force is not proportional. Let me say not in red here. The force is not proportional to theta. It's proportional to sine theta. Now, why am I comparing theta? Theta is the displacement. Right? Theta is physically the thing that we measure for angular displacement. So in order for it to be simple harmonic motion, force would have to be a direct function of theta. It's not a direct function of theta. It's a function of sine theta. Now, here's where this chart comes in, and you might recall this with the introductory assignment. You had to do approximations. I think it was in question 5, if I recall correctly. Don't quote me on that. It may not have been question 5. You had to calculate the error on sine theta within 10%. That's what you had to do. And we see here, if we introduce an approximation where sine theta equals theta, of course this is not always true. Of course sine theta does not equal theta. I mean, come on, let me just draw those two things very quickly for you. If I draw theta as a function of, I don't know, time or whatever, then that's just going to be a line, right? But if I draw sine, it looks like this. So yeah, if I want to say, is it true that sine of 2 pi approximately equals 2 pi? Is that true? Of course not. Sine of 2 pi is 0, but 2 pi is 2 pi, right? Those two things, these two things are very different. So if I want to claim that sine theta equals theta, that's only a reasonably good approximation for a very small amount of numbers or a very narrow domain. And you can see on the graph here that the first part, sine theta and theta, are approximately equal to each other. The question is, when does that start being a bad approximation? And that's what I was sort of hinting at in the intro assignment, and that's kind of what we need here. You see a chart saying when theta is 1 degree, sine theta precisely is 0.17545, and 1 degree in radians is 0.1745. They're virtually the same into 5 decimal places. At 10 degrees, well, 10 degrees converted to radians are 0.17453. And if you take the sine theta, it's 0.17365. They're different, but they're very close. They're within 0.5% of each other. And universally, we seem to agree, I guess in the collection of physicists, that 30 or even 35 degrees is roughly within a 5% uncertainty. So we deem 5% error to be a reasonable approximation. Anything beyond 5% error is kind of like, yeah, that's bad. You probably shouldn't be using that approximation. So when we say let theta equal sine theta, this is only valid for values of theta less than either 30 degrees or 35 degrees, somewhere in that range. Now, you might be asking yourself, who thought of this? Who looks at a trigonometric function and says, that is exactly equal to a line, y equals x? That is a very good question. And I will tell you that it was not done, ooh, where'd it go? That was not done by looking at a graph and saying, oh, look, the sine graph looks like a line. It was actually done through a Taylor series. Now, if you've recently taken calculus, you would have finished the class with Taylor series. So probably in like late March, you would have learned Taylor series. So they might be fresh in your head. A Taylor series, if you take a Taylor series of sine, you actually get theta minus theta cubed over 3 factorial plus theta to the 5 over 5 factorial minus theta to the 7 over 7 factorial plus, and the pattern continues. So if you take a Taylor series expansion of sine theta, then we say, well, for small values of theta, let's say theta equals 0.1. Well, what is 0.1 cubed? Well, 0.1 cubed is 0.001, and 0.1 to the 5 is 0.00001, and this one just gets even smaller. Well, this one sits here at 0.1. So for small values of theta, these are called higher order terms. For small values of theta, they're the higher order terms. They're called higher order because the degree of cube, the degree of 5, the degree of 7 just gets larger and larger and larger. So for higher order terms, theta gets smaller and smaller and smaller, right? Theta cubed is smaller than theta. Theta to the 5 is smaller than theta. Theta to the 7 is almost 0 compared to theta. So for higher order terms, we actually say this just approximates the first term, theta. So that's where the approximation sine theta equals theta comes from. So where does that leave us? There's a lot of parallels. Sorry, let me just readjust my screen here. There is a lot of parallels between the simple harmonic motion of a pendulum and a simple harmonic motion of a spring. Here, we know that the period on a spring is 2 pi times root m over k. It turns out the period on a pendulum is 2 pi times root L over G. Now, there's a lot of new equations floating around. Please think about them intuitively. With a mass on a spring, if you keep the spring the same and you increase the mass, you make the mass larger, just think to yourself intuitively. If I increase the mass, would that make the same spring push it faster or slower? Obviously, if it's the same spring and you increase the mass, it's going to go slower. So is it root m over k or is it root k over m? I can't remember. Think of it logically. As m gets bigger, the period will be longer because it takes longer. It's moving slower. That's how you remember m is on top. Same thing with L. Think of like a really, really long pendulum compared to a really short pendulum. For those of you who play a musical instrument, you can think of a metronome. A metronome, like on a lot of piano players use a metronome, tick, 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 tick. You slide the little weight on the metronome to change the length of the pendulum, and that changes the tempo. So just think to yourself, a really, really long pendulum is going to take longer to complete one cycle than compared to a short pendulum. Okay, now, part of the pre-quiz, and I'm hoping you're not yelling at me through the screen right now for the pre-quiz last minute. It's due at 10 p.m. tonight. Okay, so I knew I sprung it on you last minute. There's only 3 questions. They're all dead easy. I really, honestly, the whole point of that was I just wanted you to see the video. I had every intention on showing you the video and lecture, but I had a feeling we would run out of time, and I'm kind of right. I'm looking at the clock now, and there's only 20 minutes left of lecture, and it was a 10-minute video, so that would not have worked. So I really just wanted you to see that video. And it was a really awesome video of that MIT physics professor, Walter Lewin again. And he's older in that video. He's probably in his 60s, if not even older. And he literally cradled that pendulum like Miley Cyrus in the Wrecking Ball video. And that video came out before Miley Cyrus's Wrecking Ball video. So maybe, Walter, if you're listening to this, if you find this on YouTube, maybe you should kind of approach Miley Cyrus's lawyers and try to get some royalties from that idea, because I'm pretty sure you did it first. Walter wanted to demonstrate that even though it's intuitive to think that the heavier the pendulum, the faster or slower it would move. I mean, I guess intuitively you'd think if it's heavier, it would move slower. However, the formula does not predict this. The formula says it's not a function of theta, it's not a function of mass, it's only a function of length. And Walter really wanted to prove this. And yeah, could he have just attached a larger mass at the end of it? Yes, but that's no fun. There's no physics spirit in that. If you're not destroying something or putting your life at risk, you're not doing physics experiments right. That's kind of a false statement, but still it's fun. Most physics instructors like doing fun, destructive things in class. Anyway, so Walter got in his mid-60s, he got on this giant pendulum, and he swung back and forth while he timed himself. And he proved that it is exactly the same period when he has more than quadrupled the mass. So please watch that video, and I'll give you the answer to part 3 or question 3. He is trying to show the only variable that impacts the period of a pendulum is length. Now the other variable, which it's not really a variable, I guess it's a constant, which is why I said only variable is L. The other factor in there is gravity. And for a lot of the times, gravity is just 9.8 because we are all on the surface of the Earth. However, it is possible to sort of invent questions where, you're on Mars or you're on the moon, and gravity is different on Mars or the moon. So there are situations in which gravity, G, could be different than 9.81. So please watch out for that. Okay. So this is the conclusion here for Walter's video. As long as the chord is considered massless compared to the mass on the end, then the period is not dependent on any mass. It's only dependent on the length, which is very counterintuitive and very cool. Okay. I think we can skip this concept question because I pretty much just said the answer. 2 pendula have the same length but different masses. How do the periods compare to each other? They're the same. I just got finished saying different masses do not matter. So I think we can skip that. This one, a pendulum is suspended from the ceiling of an elevator. When the elevator is at rest, the period is measured to be t. What happens to the period when the elevator is accelerating upward? Think about what this means. Picture yourself standing in an elevator. While the elevator is rising or accelerating upwards, what do you feel? We've talked about this in forces. We've talked about the normal force. We've talked about weightlessness. While the accelerator is while the elevator is accelerating upwards, what do you feel? If the, I almost said accelerator again. Boy, I'm tired. If the elevator is accelerating upwards, then what you're doing is you're actually increasing your normal force. It'll make you feel heavier. You will have a higher apparent weight. And similarly, as the elevator is accelerating downwards, you feel lighter. That's why you get the butterflies in your stomach sometimes when the elevator descends. So we've established that the normal force is higher, which means you will feel a larger apparent weight. So you'll feel a larger apparent gravity. And if you feel a larger apparent gravity, then that means it appears as though the effective gravity, G, is larger than 9.8. So if you look at the period equation for a pendulum, root L over G, if G goes up, period goes down. Because if gravity is stronger, or the apparent gravity is stronger, then it will oscillate quicker, meaning period will go down. It takes less time to complete one cycle because it's oscillating quicker. Okay, next one. You are sitting on a swing. A friend gives you a push and you start swinging with period T1. Suppose you were standing on the swing rather than sitting. I'm sure we've all done this before. We were all teenagers once. Some of you might still be 19 or something, but when I say teenagers, I mean like 13. Hell, I don't know. Maybe you stand on the swing when you're 19. I don't know. I don't want to make any assumptions. So suppose you were standing on a swing rather than sitting. When the same person gives you the same force of push, you start swinging with period T2. Which of the following is true? So I won't launch the poll. I just want you to think about it. So there's the formula for the period of a pendulum, 2 pi times root L over G. Walter, in his video, did mention this. He said, but a sharp student will realize that if I sit on the pendulum, my mass, the human body's mass, will be above the mass of the ball, and that will shorten the effective length of the pendulum. And then he said, I know this as well. And that's why if you watch the video, Walter had to lean back and plank. He is probably one of the oldest people I'm aware of who is able to plank for such a length of time, let alone swinging on a pendulum. That is absolutely amazing. Anyway, so Walter had to plank so the mass that he added to his pendulum was at the same length as the old mass was added at. So here, if you stand on the pendulum, you're not adding the mass at the bottom, you're in fact adding the mass kind of up. So what you're doing is you're actually decreasing the effective length because you're changing the location of where you've added the mass. You've added the mass higher up, which means the length of the pendulum, the effective length of the pendulum is shorter. Recall our discussion of center of mass. This is why center of mass is important. So as long as you can understand you're raising the center of mass, you're shortening the length between the mass and the pivot point. So if you decrease the length, what you're doing is you're decreasing the period, meaning it takes longer. Wait, what's happening? If you're decreasing the length, what does this say? L1 is longer than L2. So, oh yeah, that's what yeah. If L, yeah, so sorry, I'm getting myself mixed up. It takes longer. If it takes longer, then your LL, if L1 is bigger than L2, then T1 is bigger than T2. That's what I was. 2 goes down compared, oops, compared to T1. So there you go. This means that T1 is larger than T2. So that actually means you speed it up. My apologies, I got that backwards. So I got the value of T correct, I just interpreted it incorrectly. So if L goes down, T goes down, and if T goes down, that means the period goes down, means you're speeding up. It takes less time to complete a period. So if you stand up on a swing, you'll end up going faster, is what this question says. Okay, so we have about 15 minutes left. Let's do one question together. I have 2 example questions here. Let's do one of them together. Let's do this one, because I made this one last night, and I took the other one from a textbook, and textbook questions are fine, but they're kind of boring. This one I made last night, so let's do this one. So, say mankind has finally colonized the moon. You know, there's a lot of movies about colonizing the moon. Interstellar, I think, is about colonizing Mars, but let's pretend we can colonize the moon. There's no water on the moon, so like it would be an incredibly hard task to do, but let's say we can do it. If we did colonize the moon, of course it would be thanks to Elon Musk, because, I mean, come on, the SpaceX launch that just happened. He would definitely be the first to do it. However, Elon Musk hasn't figured out power generation yet. He's just figuring out like oxygen supply and food supply. He's going to figure out electricity later because he knows physics. He can deal with that later. In the meantime, though, he needs to keep track of time. You know, his watch might work. He probably has a smartwatch, I'm guessing. His smartwatch would run out of batteries pretty quick, and there's no electricity on the moon, so you can't charge a smartwatch. So how do you keep time on the moon without electricity? This is where a grandfather clock comes in. So a grandfather clock, for those of you who don't know, you have the clock face kind of up here, and you have a pendulum down below that swings back and forth, back and forth, back and forth. And as it swings back and forth, back and forth, back and forth, it rotates cogs in the clock, and you know that's what drives the clock forward. That's what keeps the time. So this pendulum in a grandfather clock has to be calibrated perfectly. Because if it was too long or too short, it would oscillate at not 1 second, and it wouldn't keep time properly. It would either be too fast or too slow. So the goal is to have each swing of the pendulum 1 second. That is the goal. So the goal of a grandfather clock, GFC, is for each swing to be 1 second, meaning 1 second this way, 1 second that way. So tick, tock, tick, tock. Each tick, 1 second, each tock, 1 second. So tick tock is 2 seconds. So this tells me that the period of oscillation, the period of oscillation has to be 2 seconds. Forward, back. That's one period, forward, back. So 2 seconds. So pendulum, period, equals 2 pi root L over G. We know the period has to be 2 seconds. Now, we need to solve for the length. Elon Musk himself has to build this clock. So what is the length of this grandfather clock on the moon so he can keep proper time? Well, obviously the gravity on the moon is not 9.8. That's the gravity here on Earth, and Earth is much, 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 much bigger than the moon. So the gravity will be different. Now, a quick Google search will tell you that the moon's radius is about 27% that of the Earth's radius, or a quarter, just to keep things approximate. So you can say the radius of the moon equals the radius of the Earth over 4. So with this, you can actually, you also need the mass of the moon as well. I forgot to Google the mass of the moon. That was my bad. But you can get a relationship between the mass of the moon and the mass of the Earth as well. It's going to be some fraction times the mass of the Earth. Now, it turns out when you do that, you can calculate the force of gravity equals mass times g, mass of the moon over radius of the moon squared. It turns out that is actually going to give you about 1/6 the gravity on Earth. So you would plug everything else in, you'd say mass g, mass of the moon is going to be some fraction times the mass of the Earth. And the radius of the moon is going to be 1/4 the radius of the Earth. So you're going to end up getting some sort of constant times g. And I'm telling you now, the ratio is about 1/6. It's a well-known ratio between moon and Earth. It's about 1/6 the strong for gravity. So I guess that would make K 16/6. But anyway, you could look up the mass of the the moon later if you want. Anyway, point being, we know that G is going to be about 1/6 of 9.8. So here we can actually solve for the length of the desired pendulum. So the length of the desired pendulum is going to be, let's see, let's square everything. So 1 equals pi squared L over G. So that means L is going to equal G over pi squared. Oh, no, I forgot the 6. G over 6. There we go. Okay. So that is how you would solve for the length of a grandfather pendulum on the moon if we happen to magically colonize the moon and live on the moon. And some weird alternate universe where we also didn't have electricity on the moon, but we could somehow figure out how to breathe. I don't know. Go with it. Okay, anyway. That's all there is with simple harmonic motion. It's fairly simple. In summary, with simple harmonic motion, you can measure it using a cosine graph or a sort of cosine function. We have properties of the wave. We have period, frequency, amplitude, things like that. We've got a notion of what a cycle is. We have a formula for measuring the period, both on a spring system as well as a pendulum. We know properties of the motion. It's got a maximum speed in the middle, a maximum acceleration at the ends. They're never zero at the same time. You know, it's simple harmonic motion. There is not a lot to it other than pretty much what we just talked about. In the last 7 minutes, we're going to cover some basic properties of waves. Oscillations are one way to interpret waves, but waves in general is a fairly large topic, and it doesn't, like, all waves is a type of oscillation, not always as intuitive as, say, a mass going back and forth on a spring or a pendulum oscillating back and forth. As we can see here in the picture, waves can be created, let's say, in water. And you can see at the surface of the water here that it follows a sort of a sinusoidal function as well. So the topic of waves is quite broad, and it all hinges, no pun intended, it all hinges on the same analysis we just developed for simple harmonic motion. They all have a rooting in sine and cosine representations. So let's look at other kinds of waves. This relates to the lab 4, I believe, standing waves on a string. So let's see how far we can get in like 6 or 10 minutes. We might go a few minutes over time. Hopefully that's okay. So for those of you who go to the gym, which I've never been to the gym ever, it probably shows. I get winded walking upstairs. Anyway, for those of you who go to the gym, you might have seen these really heavy weight training ropes, and you can send wave pulses down the ropes. So when you're training, literally your entire job is to send wave pulses down ropes. You're doing a physicist's job while going to the gym. That probably should be incentive enough for me to go to the gym, but anyway. So that's kind of what we're thinking about here. If you were talking about a wave pulse, let's say in water or a string, this is what a wave pulse is. It's when you send a wave kind of down a string. So that's what's happening here. You pull the end of the string up, and then you kind of shoot it downwards, and then that sort of wave pulse travels forward with time. So we have forward motion with this kind of wave as well. Simple harmonic motion, we didn't really have forward motion. We just had oscillatory motion. It moved forward, then moved backwards, moved forward, then moved backwards. So the system doesn't really go anywhere. With a wave pulse in water or a string, there is forward motion. We have very similar characteristics. We have amplitude, wavelength now I'm introducing. Wavelength is the physical distance between peak to peak. So that could be 1 meter, that could be 6 meters, that could be a centimeter. So you can think of the wavelength as analogous to sort of the period, sort of. The period is the time at which it takes to go from peak to peak. The wavelength is the distance at which it goes from peak to peak. Okay, there are two types of these waves. There's something called a longitudinal and a transverse wave. So a transverse wave, our brains are very familiar with. This is a transverse wave. Why is it called transverse? Well, we have this equilibrium position where y is equal to 0, and a transverse wave occurs when you cross the equilibrium position. That's a transverse wave. A longitudinal wave is when you have a wave that propagates by colliding horizontally into its neighbor. So for instance, if you, it might not be very intuitive to show you in a picture with a spring, but a more intuitive, I'll come back to that in a second, a more intuitive understanding of a longitudinal wave might be something like air or sound. So for instance, when you talk or you turn on a speaker, what you're doing is, if this is the speaker or a drum or your vocal cords, you're jiggling the air molecules that are physically touching the speaker or your vocal cords or the drum, and you jiggle them back and forth. But what happens here is the jiggling hits its neighbors, and the way the wave propagates forward is a series of collisions that carry the collision forward. And that is called longitudinal, because the wave is actually not, it's like this type of wave, there is no oscillation up and down. The string is not moving up and down. The air particles are not moving, up and then down. The air molecules are jiggling left and right, and as they jiggle left and right, they are colliding into their neighbors, and then there's momentum transfer that happens, which we've studied, and then it keeps going from on and on and on. That's what a longitudinal wave is. Okay, now here is a question. I won't launch the poll for time reasons. At a football game, we do a wave like woo. We do a wave to cheer in the grandstand. It might circulate through the stands and move around the stadium. In this wave motion, people are known to stand up and then sit down as the wave passes. What type of motion is characterized by this motion? Now, if people stand up and then sit down, right? They go up and then they go down. That is going to be a transverse wave because there's actually motion up and down. The way the wave propagates is not through punching the person next to you, right? You're literally standing up and then going down. So you have this sort of crossing of the equilibrium position. That's why it's transverse. Okay, reflection and transmission of waves. If you send a wave pulse forward let's say a piece of string, if you nail the piece of string at the end, then as the wave pulse is moving forward, it'll run into this nail and it'll try to pull the nail up, but the nail won't move because the nail is nailed into a piece of wood. So if you try to pull up on something that doesn't move, what you're actually doing is you're pushing yourself down. If you don't believe me, try grabbing your car. Go to your car and lift up your car. Your car obviously will not be lifted, and if it does, please give me a call. You and I have some stuff to talk about. But if you try to lift up your car will just push you right into the ground. So that's what happens here. As it gets to the end, it tries to pull up on the nail doesn't move. So the whole thing flips upside down, and now it's upside down because the nail is pushing the string into the ground, and then it's got nowhere to go but backwards. So that's what we call reflection. A wave pulse hits a wall or hits a fixed point and then inverts and reflects backwards. Now, if the wave pulse hits an end, then if it's a free end and it's not nailed in, then as it approaches the end is actually free to lift. The nail, it was not free to lift. This is free to lift. So when it reaches the end, this will just come up and then fall back down, and as it falls back down, the wave will go back, but not be inverted. So on this slide, there's two things. Reflection happens. If the wave pulse moves forwards, it will be reflected backwards. However, there are two ways that can happen. If it hits a fixed end, it'll reflect inverted. If it hits a free end, it'll reflect not inverted. Now, it doesn't have to just hit a wall. If it transfers into a new medium, let's say a heavy section or a heavier string, then when the wave pulse comes this way, it's a partial wall. A partial wall means when it reflects, it will be upside down, inverted. But it's a string, not a wall, so part of it will go through. And when it goes through, it will maintain its initial orientation, right? Because as it comes this way, it will pull up on this string a little bit. So the wave pulse will be not inverted, it'll be erect, and it'll travel through. But part of the energy will be reflected backwards. You can think of this like momentum. Picture a light object, a ping pong ball or a tennis ball, hitting a car. If you throw a ping pong ball at a car, well, let's assume it's frictionless. You throw a tennis ball or a ping pong ball at a car, the tennis ball comes back. It reflects backwards. But part of the collision, part of the momentum is transferred to the car, and assuming there's no friction, the car will actually travel forward in the original direction. That's what's happening here. So there's a parallel here, parallel with momentum collisions. Okay. We'll get into this a little bit tomorrow when we talk about sound. I want to just, before I let you go, I just want to mention a few more things. The nice part about waves is they can interfere with each other, and it's called superposition. So if you have a wave pulse traveling to the left that has an amplitude of A, and you have a wave pulse, oh sorry, that's to the right, my apologies. If you have a wave pulse traveling to the right with amplitude A, and a wave pulse traveling to the left with amplitude negative A, then when they meet in the middle, they're going to meet somewhere in the middle, they will perfectly cancel out. So for a very brief moment in time, it'll look like this wave or the string is completely flat for a very brief moment in time. And then a split second later, the erect wave that used to be on the left will continue forward, and now the erect wave will be on the right, traveling to the right, and the inverted wave will be on the left, traveling to the left. The opposite is also true. If you have two erect waves that kind of meet in the middle, then they're going to what we call constructively interfere, and the amplitudes are added, and this amplitude is 2A. And then after, they're just going to pass right through each other and go like this. Superposition is actually the foundation of quantum mechanics. So for those of you who have taken a chemistry class, we assume electrons are waves, and you know, when they interfere with each other, they can superimpose on one another. So quantum mechanics is actually really cool for that exact premise for the superposition. So that's what this is saying here. If you have two waves that superimpose, they get really big. If you have two waves that deconstruct, they add to give 0. And this, that, the other thing. So that's not that hard. And the very, very, very last thing I want to say before letting you go is, what is a standing wave? Because and the reason why I'm pushing through 5 minutes late is because you need this for your lab. So please hang with me, this is for your lab. What is a standing wave? A standing wave occurs when you send a wave pulse down the string, and when it gets reflected backwards, but you don't just send one wave pulse down the string, you keep sending wave pulses down the string. You're repeatedly jiggling the string. So you're sending many, many wave pulses down the string, one after another in succession. And then eventually they will hit the end and they will invert, and then they will come backwards. Now, all sorts of weird patterns can happen, right? Because you're constantly sending new wave pulses down, you're constantly getting reflected wave pulses back. The superposition of this could be any number of patterns, messy patterns. However, a standing wave is a wave in which you have exactly the perfect frequency, where when you send wave pulses down, they superimpose and they constructively interfere and they make a really nice pattern. That is what a standing wave is when the reflected waves are in phase and constructively interfere, and you get this really nice superposition pattern. So you can shake it lightly and get a pattern like this. You can shake it a little bit faster and get a nicer, a different pattern with one node. You can shake it really fast and get 3 nodes. And the lab 4, is developing the formula around what governs this. And the formula is dead simple. All it does is it looks at the length of the string and compares it to and relates it to the required wavelength. So here, if we have no nodes, the only nodes are at the end, so there's no nodes in the middle, then what is this? Well, if you were to complete the wave, this would be like a sine wave, for instance. We see here that the wavelength lambda is in fact twice the length of the string. The string only goes from here, but the whole wave is actually the whole thing. So this is in fact 2 times the length. Or if you solve for L, you say L equals lambda over 2, which is exactly what this says. Similarly, here, if you have 1 node in the middle, what's the wavelength of the wave compared to the length of the string? They're equal to each other. If you have 3 nodes, well, if you have 3 nodes, here is lambda. So this extra bit is half a lambda. So here, the length of your string is actually 1.5 lambda, or 3 over 2 lambda. That's the premise of standing waves. Everything is encompassed in that exact idea, is counting how many nodes, comparing the wavelength of the wave to the length of the string. You will see that there's a pattern here. The pattern is, well, let's solve for lambda here. Lambda 1 is going to equal to 2L. Lambda 2 is equal to L. Lambda 3 is equal to, let's see here, 2L over 3. So this can be 2L over L, 2L over 2. So the pattern seems to be, that's weird. The pattern seems to be 2L over N for lambda N. N is the number of nodes. Or sorry, N is the number of nodes plus 1. So we can actually relate lambda and frequency using the wave equation. The wave equation is coming up. Oh no, I think we may have passed it. The wave equation is V equals F lambda. And this is just dead simple. I know we were 10 after. This is literally the last thing I'm going to say. This is the wave equation. It's deadly simple to get. It comes from V equals D over T. The distance of one period is lambda. And the time it takes for one period is capital T. and period and frequency are inverses from one another. So we can say lambda instead of t. So that's where the equation v equals f lambda comes in. So lambda is very intuitive to relate to the length of the wire. Using the wave equation, you can relate lambda and frequency, and then bam, you have your equation in the lab, practically. I know the equation in the lab deals with the tension force and all this stuff. It's a little bit different, but this is the main gist in the lab right there. And the n is what we call the harmonic number. So the fundamental frequency is when n is equal to 1, and then we have a second harmonic, third harmonic, and that's when you increase the number of nodes by 1. Okay, we will start off tomorrow's class perhaps with an example, and then we're going to move on to sound. But that'll be all for today. So thanks for sticking 10 minutes extra. I just wanted to make sure that you guys had a better foundation for your lab. I know some of you have your labs due today in about 50 minutes, but hopefully that kind of helped you give some context. Okay, so that's all for today. Thanks for reaching the end. And I'm going to stop the recording now and take some questions.